Hello and
Okay.
welcome to IABSE in Conversation, where I, David Knight, talk to eminent and interesting designers and structural engineers about what inspires them in their life and career. In this episode, I'm delighted to welcome Bill Harvey as my guest. Unfortunately, due to technical issues, this episode is in two parts. However, I hope you find both very interesting. Bill is a structural engineer with a career that has covered a huge breadth of the bridge industry, from groundbreaking material research to site roles on extremely long-span structures to his current passion for masonry structures. So, Bill, where did all this start? You grew up in and around Yorkshire in the 50s. Was there a particular experience in your childhood that pushed you into a career as an engineer?
Yes, my mother's family came from Bristol, and we used to travel down to Bristol for family holidays. And one year when I was 7, one of my uncles took me to the Clifton Suspension Bridge. And I can still remember poking my head through the railings and looking at the tiny people down below. You can't do that anymore. And thinking, in modern terms, because those words weren't used in those days, how cool is this? This is what I want to do.
It's an inspiring project, isn't it? And we'll come on to it a bit later because
It
you've
is, and
worked on it as your.
you learn more about it as time goes on. And I'm just going to kill a program here for the time being because it keeps pinging at me, and I can't work out how to stop it.
No worries.
Yes, and then I was lucky that my mother's father was a site foreman, and when I said I wanted to build bridges, he said, well, in that case, you want to be an engineer, and that means you need to go to university, which was a sort of new concept in our family, certainly.
And
But that took me through things like 11 plus and stuff like that. Yeah.
And sort of reading through your CV, it's impossible really to know where to start. You've done so much and been through multiple careers, I think you've mentioned to me in the past. However, there's sort of four great bridges that stand out: Humber, Cadell, Aberfelding, Clifton. But you started your career after university, firstly at Leeds Council. What was that like as an experience?
Both at the time and in retrospect, very interesting. So as a bridge engineer and declared bridge engineer, they put me on the roads department first. So it was an 8-month session milk round, But that was fun because I went out on site as a junior engineer in a supervisory role, sort of just watching what the contractor was up to. A number of interesting features of it, including the fact that there was a clerk of works who was responsible for keeping records on part of the job, but he was off sick at one point, and I inherited his job as well, which was interesting and challenging. So I had 8 months on a construction site, learning things like walking back to the office one day and finding a man with a vibrating roller at the bottom of a 3-meter deep trench, and just, what do I do about this? And that sort of feeling has stayed with me ever since. It reinforced it established the thought that you can't trust anyone. Yeah, that you have to have eyes in the back of your head. You have to be looking out for all other people, and you have to accept that it's your responsibility, not only to keep yourself safe, but to keep everybody else safe. And that was an interesting and worthwhile lesson. And then I moved from there to the sewage works, working in the main drainage department in a design office again, and we were working on lots of new extensions to Nostrop sewage works in Leeds, which hadn't been touched since Victorian times. And one part of that was the interesting thing of working with people who really cared about what they were doing. My immediate boss, when I first arrived, said, first time it rains, put your coat on and wait by the door. And I did that, and he came and collected me, and we dashed across to the inlet weir, where there was all the effluent of Leeds running through a wooden trough, which I suppose was about 3 meters wide and 1 meter deep, across the middle of this big brick pit, which had 2 enormous tunnels going out of it. And we stood there for 5 minutes, and suddenly this timber trough just overflowed and filled the chamber. And these 2 tunnels were discharging raw effluent from Leeds straight into the River Aire, because the flow was too great for the sewage works. But when that was first done, it was okay, because the dilution in the river was fine-ish.
Yes.
with all that rainwater with it as well. But by the time we were working there, it was definitely not fine. And the pressure was to get stuff built that would treat that extra effluent. So that was interesting, and a diversion, and learning that people really care about what they're doing was good. Then I got in the Bridges office and got bored out of my skull, which is really strange.
In retrospect, especially, given the rest of your career.
Yeah, and very frustrating. So an early experience was being asked. In fact, the first job I was given was to check some calculations on a bridge abutment, and it got to the HB load thing, and the vehicle ran down the side of the bridge, and I went back to the boss and I said, "You haven't allowed for the lateral overturning of this load off centre that's going to increase the load in the piles by 10%. And he said, "No, it doesn't. The load distributes at 45 degrees through a wall, and 45 degrees encompass the whole of the base, so it's a UDL across the base." No, that's not in equilibrium. It doesn't work like that. And in the end, he said, well, I said to him that if you're telling me it doesn't matter, fine. But I just need to get it on record that this isn't right. And in the end, he said, well, actually, I just don't understand what you're talking about, so we'll just ignore it. At which point I decided I had to go.
Yeah, it's an interesting point of reflection, I suppose, for people who do have those, who perhaps have staff who work for them who have to respond to those questions. And it's a point at which, as a senior member of staff, you can teach. And I'm sort of intrigued by your response in that situation, but also the sort of your ongoing involvement in education and teaching, and engaging young engineers in the way that in improving their understanding of engineering through those episodes.
Yeah, without understanding, engineering is nothing. Really, it's just a route to disaster.
But also, you know, talk about Leeds, but talking actually really about being more on the contracting side, or enjoying more the contracting side. And after that experience, you went to work I'm not sure whether it was immediately, but on the Humber Bridge during construction.
Yeah, I went straight from there to Humber Bridge, working for Freeman Fox. So again, I was working for the gamekeeper, if you like. And that was also frustrating. I was there for 18 months. Fascinating, working on a massive site, huge things, and seeing stuff done just really actually not competently, some of it. So I was working in the Hesel anchorage, which is basically just a massive block of concrete held together with reinforcement, and then you attach a couple of wire cables to it and pull with 19,000 tons. And so if you've ever tried pitching a tent on rocky ground and putting stones on the end of the guys, you'll know how hard it is to hold those guys down, which is essentially what we were doing. And Freeman's had detailed the reinforcement just as long straight bars. So, yeah, the abutment was 40 meters high. From the foundation to the top is about 40 meters. And they just detailed 40mm bars vertically through this whole height. They detailed laps top and bottom and 2 L bars to go underneath, but the joints through the height were to be left to the contractor, and it was a sound thing to do, because pitching 40mm bars is hard. And the contractor had the bars delivered in 6-meter lengths, which meant that if you put the pour levels at the first one a little below, but after that at 3 meters, then every bar that you had to splice would sit straight on the concrete. And they never bothered about persuading the joiners to put the top marker for the concrete at those levels. And at one point, the steel fixers were lifting 6-meter long 40mm bars and having to hold them 1.5 meters above the ground and lash them on. And this sort of disjoint between what was detailed in the office and what was carried out on site, I found fascinating. And that was, it's both very hard work and very dangerous, actually. A 6-meter length of 40mm bar, I can't remember the numbers anymore, it's about 100 kilos. And lifting that 3 meters is hard. Then getting it up vertical and lifting it another 1.5 meters, just forget it. So every bar had to be going on the end of a crane. And the cost of that is just astronomical, absolutely astronomical. So all sorts of things to do with that.
It sounds like a formative part of your engineering training, the sort of the understanding immediately after your university education of what the reality of working on site is, and what issues drive or should be driving designs back in the office.
Yeah, and working on big stuff, it's particularly in your face because there's no escape from the fact that this is big and heavy and difficult to handle. And when things are relatively small and not so heavy, being difficult to handle isn't the end of the world. Or at least the men can make it look too easy and you don't notice that it's actually difficult.
Did you have a particular challenge? Was there something on that site that you thought, oh, that gave me sleepless nights at the end of it?
There were 2 or 3 things. There was one thing where I had to intervene, which was an interesting, actually a couple of things where I had to intervene, which was an interesting challenge. So I was working on the anchorage. The towers were the first concrete towers that had been used for a suspension bridge. And that was because Freemans had previously had their fingers burnt with steel erectors putting the towers up and holding jobs up. And the contractor decided to slip form them, which was pretty demanding because slip forming at that time was something that you tended to do with silos. So long runs of 9-inch wall. And this was a 6-meter square, more or less solid block of concrete. There was a hole in the middle for a lift, and colossal amounts of reinforcement. So in a typical slip form job, the reinforcement is nothing bigger than about 12mm. Here there were 50mm bars, and in places there were 50mm bars at 150 centres in 3 layers around each face. So handling that was quite a business. Tilemans, who were the subcontractors to do the job, were superb, but they arrived on site with a platform which was the working platform for everything. And it was fabricated tubular base frame, basically. And I happened to pass it one day, and I noticed that as they were bolting the pieces together, some of the welds were springing open. And I looked a bit closer, and I thought, I'm not prepared to go on that. And really, nobody else should be prepared to go on that. And it was necessary to say, this won't do. And given that the job was already sort of 6 months behind, saying this won't do wasn't entirely popular, let's put it that way. But it was very interesting. Freeman's called in sandbergs to look at the welds. And I happened to be down at that part of the site when the sandberg man was there because I was interested. And the guy from Tarman's was hovering over his shoulder and saying, could you just mark up the welds that we need to cut out? And he said, well, looking at this, it'll be quicker to mark the ones you can leave.
Wow. That's a big job.
And, it truly was just rubbish. I mean, I'd never looked at weld before, but it was so obviously not competent welding. And they had to get in a gang of welders, and there were 3,000 or 4,000 joints re-weld.
Wow. Extraordinary. But after that experience, and this is very early on in your career still, you moved back into academia, I think in 1977. You'd taken a PhD at Leeds and went back to a lecturer position at the University of Dundee. What drew you back into academia after a few years of excitement on big bridge science?
Well, if I just slot a few things in between there, first of all. So I got bored with the Humber Bridge stuff because people were doing things wrong and I couldn't do anything about it. All I could do was say, no, that's not good enough. And money was running out because Freeman's were not the best payers. And I moved down the road to the Is Bridge working for the contractor. And I had 18 months on the Is Bridge, basically just putting a concrete deck on a steel bridge as the bridge went up, but working alongside all the steel people and so on, and working with some very old foremen, which was good, real learning experience. And another thing that happened there was, once again, my section foreman went sick and he was off for 3 months. So I found myself running a section with, I suppose, about 100 workmen for 3 months and having to do the whole bit, including banging on the cabin door and saying, come on guys, it stopped raining, time to get out and do some work.
I'm glad to see sites haven't changed very much in that long time.
When the foreman came back, I said to him, how long does it take to get used to banging on the door and saying, come on out guys? He said, never. You will never ever get used to it. He said, especially if, as happened to me fairly early in my foreman career, you bang on the door and say, come on, it's time to get out. And the door swings open and you get a fist on the end of your nose. I'm glad he didn't tell me that beforehand. So that was 18 months. Then I did 6 months in Dunkeld with Redmond Dorman Long on an 800-ton free-span bridge built on the riverbank and launched, and that was interesting, exciting work. From there, ran out of site work and moved to Bedford to the estimating office. I was then put temporarily back on Humber for 6 months, working on the contractor side, working on the erection of the footbridges. But the boss would not confirm that I was likely to stay there for a length of time, and my kids were starting school, so it was time to find something a little more stable so that they could stay in one place. So I had to give up my dream job and start a new career in something which had never really occurred to me as a possibility, but there we go. In bridge design at that time would have meant going to London, and I really wasn't interested. I'd done the local authority thing, and although there were some very good local authorities to work for in retrospect, and there were also some bridge consultants elsewhere, like Glasgow, for example, which were really good. But yeah, the university seemed to be a possibility, and I'd done a bit of teaching off and on and enjoyed it, so that sounded good.
So that's interesting. Education's we've mentioned, but it is obviously a passion of yours through the 23 years you spent lecturer and professor at Dundee and then Exeter. I'd even argue that your communication, or continued communication through Twitter, is an extension of this. That need to educate people is sort of, it's fascinating, and it must be formative in, or interesting in the way that you think about engineering. Have you changed that approach over the years? Have things improved in the way that teaching works, or that you teach people over that time frame?
The way I teach people, let's start there. One of the interesting things, well, the first thing to say is that teaching is addictive. Right? If you find that if you see people going away having learned something, that's an addictive thing. And the whole Twitter piece is just about not being able to give up, not being able to survive without that addiction. One of the things that it takes a while to learn is that no two people's brains work in the same way. So that the way you understand something may not be actually understandable by somebody else, and you've got to keep trying to find new ways of understanding where you can convey ideas, and that is a fascinating challenge, finding new ways of looking at things. And one way that I had it described to me was that if you think in terms of structures, there are people who see it in terms of pictures, there are people who see it in terms of maths, and there are people to whom it means absolutely nothing if they haven't got a picture in their mind of the finished product. And in any one class, you're going to find all three of those groups, and you're going to have to reach all of them. And that's an interesting challenge, and it's something that you have to learn. You know, it takes a long time to realise that, or it can take a long time to realise that the reason you're missing this whole group of people is you're just not talking their language.
And it takes, I think, engineers a little minute sometimes to realise that teaching is as developed and as difficult a skill as engineering is, and it takes practice, and it takes review of process and review of, well, did that work? Can I iterate on that? And all of these things that we associate with our engineering role are equally applicable often to teaching. We sometimes forget that.
This is a point to risk going off on one, as they say, but I wrote a piece the other day because I'd been awake because I was uncomfortable at 3 o'clock in the morning, and I usually listen to podcasts at that time. And I listened to a podcast of In Our Time, talking about Hannah Arendt, who was a German-Jewish philosopher born in 1906, escaped to America in the very early 1940s, before the real push of the Holocaust got going. But she was present at the trial of Adolf Eichmann, which I remember. So very early 1960s, the Mossad found Eichmann in South America and kidnapped him, basically, and took him back to. And she'd referred to the banality of evil and created an absolute storm because people just looked at the word and didn't think about what she meant. But what she meant was very closely connected to what you were just saying, is the business of introspection, the business of thinking about what you're doing and what its implications are. And the point she was making was that Eichmann was one of those very rare people who has no introspection. He had no self-awareness whatsoever. So that he, in his trial, he thought that he had a good case of mitigation on the grounds that he'd reduced the number of people he crammed onto the trains going to Auschwitz that he killed. He was still sending them to Auschwitz, but he was just not crowding them quite so tight on the trains. And yeah, so there's that business of introspection. And one of my real worries about engineering is that it's disappearing. and that far too many young engineers are being given stuff to do and actually actively discouraged from thinking about the implications of what they're doing.
We need to continue to reflect on our practice, and the practice is not just doing the numbers. It's how do we work, how do we think, how do we make that process better. And that, I think that, as you say, is sometimes lost in the education of an engineer. It's that they're teaching them how to make themselves better, rather than just assuming that they're the complete article.
Yeah, I mean, there's a sense in which it's the only thing that matters. It's the education. It is learning how to learn and keep understanding.
Yes.
The rest is just teaching, which is different.
Yeah. So while you were at Dundee, you were instrumental in the design and construction of the first, I believe, the first major composite bridge in the UK, and I think it remains the only plastic bridge, or significant plastic bridge, for a very long time, and may still be the longest span plastic bridge. How did the project come about? What was going on that led you to be involved?
Oh, the usual sort of chance. The university in Dundee had the usual sports facilities, and one of the people who ran those played golf at Aberfeldy. Aberfeldy Golf Club was a 9-hole course on the banks of the Tay, wedged between the Tay and the village. They wanted to expand to 18 holes. The only way was to go across the river. The bridge across the river was 200 years old, single track, traffic lights. The planners said there's no way you're building a golf course split between these two sides and having golf trolleys going across that bridge. If you want to do it, okay, but you've got to build your own bridge. So I got this phone call saying, could I help? And being a fool, I said, let's see what we can do. So at that time I was running a bridge design course for the final year students, and I suggested to them that this would be a good design project to work on, that we could divide into groups and do bits of the work and so on, and that if they were game for it, it would probably need building in the summer, and if they were prepared to give up their last summer vacation before they started work, then maybe we could build it. And that's how, and we were just getting going with that when a friend of mine, Peter Hewlett, said, have you thought of talking to Maunsell's, because they're into structural plastics and they would probably be interested in joining in with this project and making it work. So Maunsell brought along their expertise, they brought along their contacts, and arranged for lots of free materials and stuff like that. And the students got to see both sides of design, really. Yeah. As did I. But they got to see the business of teasing at problems that's, and it's particularly difficult with that composite. I mean, most of the material was 3 millimeter thick, mass reinforced polyester. It had a lot of glass. I mean, it was like 70% glass, I think. Just enough polyester to stick it together, not like building a boat. But it was only 3 millimeters thick. And getting significant forces into 3 millimeter thick stuff is interesting and challenging. And that sort of heightened challenge is a very good learning experience. Yeah, when it's a piece of steel, yeah, okay, we can just make it a bit thicker here, and put a bigger weld in here or whatever. When it's a standard section and it's 3 millimeters thick and you want to put the odd ton into it at a point, then it becomes a little more challenging.
And it sounds like an incredible learning process for the students, but also for you. It was a...
I still have the scars.
Well, I went to see it a year or so ago on a trip up to Scotland, and it's still standing. But it must have been quite extraordinary to to build in that location, very fast-flowing, high-rising river. Scottish summer, yes, but still probably quite inclement occasionally. Was it something the students relished? Or
It
was
rained most of the summer. Inclement's a good word. Yeah, the students. I think the students enjoyed it. It went on longer than it should have done, and we, had to find more students and different students and teach them, bring them up to speed. So on. There were a couple of girls came from Darmstadt. Darmstadt? Yeah, Darmstadt. I'd been to a conference in Darmstadt, and I wrote to the prof there and said, "Have you got any students who might be interested in coming and joining in?" And there were two girls who came from there and joined the party.
I suppose that's one way of running a contracting firm, is to employ students on their holidays.
Yeah. And actually, there are a number of things that made it possible. So the first was, and it's something that I knew and therefore was able to make use of, was that Aberfeld is a very rural area, and the school serves an area which is probably 50 miles radius. So a lot of the kids have to stay in Aberfeld, and certainly there were hostels in Aberfeld where the school kids stayed, and they were all away, so we were able to stay in the hostel. We made an arrangement with the school hostel and stayed there, and the golf club paid for that. So there was no accommodation to pay for.
Fantastic summer camp.
Yeah, yeah, a summer camp, but a fairly strenuous one. but there were just so many things. Things that seem almost trivial, like the fact that the morsel sections were designed to be slotted together. And they were designed not to be glued together. They were designed to be just held together by little dog bone shaped keys. But we needed a shear connection between the parts, so they had to be bonded. And nobody thought about the fact that if you put adhesive in this joint, it gets bigger, and therefore the dog bone doesn't want to go in. Yeah. So we arrive on site with this stuff, having been told that you just slip the end of this dog bone in and then tap it with a mallet and it will go in. Well, we went from a mallet to a 2-pound lump hammer to a 15-pound wooden beetle, with a 3-foot long hole. And in the end, we had 4 people with a railway sleeper hanging from ropes to drive this thing into place. Now, that's a different scale of operation.
by a couple of orders of magnitude.
Yeah. And it was interesting working out why that the problem was static friction. Once you broke the static friction, it would go. But anything small, the impulse was gone by the time you'd broken the static friction. Whereas with a big railway sleeper, you could go fairly gently and it would break the static friction and carry on moving. And you could get maybe half a metre at a time with that, whereas you were getting a centimetre at a time with anything smaller.
So we mentioned you left academia to set up independent consulting practice in about 2000, and it was sort of through this that you became best known for your work on masonry structures, from arch behaviour through to some serious work on the abutment walls and Clifton suspension bridge. What is it about masonry that keeps you intrigued and keeps you excited about how you can develop your knowledge and the industry's knowledge of it?
That really is a good question, isn't it? One layer of it is that far too many engineers think it's a black art, and it isn't. It's actually relatively simple engineering, but you have to engage your brain with the engineering. And the big thing about it is that you cannot get away with that two-dimensional thinking. The arch in itself isn't the whole structure anyway, although people like to think of it that way. But even if it was, it inescapably occupies 3D space. So you've got a membrane, so it has physical width, continuous width, and it goes up and back down again. So it occupies 3D space and it works in 3D space, and there's just no escape from that. And understanding how they work, we're a long way away yet. We really are. And every time I begin to get a little bit complacent, something comes along from left field and hits me on the side and says, you think you understand these things, do you? Back here, where did this come from? And for the last, 10 years, I suppose, I've been niggling away at a problem which started to show on viaducts. And it had been developing for 10 or 15 years, and people had been, in my view, misdiagnosing what the problem was. But when I began to understand what was happening, I realized that part of the issue was that I'd come up with a scheme for, you'd hardly call it analysing, but working out where the forces might go and how they might balance in these viaducts. And I knew at some levels that it was wrong, but was okay. But it was becoming obvious that it was wrong in a way that wasn't okay. And I had to get to the bottom of why. And that's a really interesting challenge. And it's an interesting challenge for an engineer to have to stand up and say, I got this wrong.
Yeah.
And perhaps more interesting is the fact that quite a few of the engineers I come across who are involved in bridge assessment really don't want to know that. Yeah? Are you telling me that everything I've done for the last 20 years is wrong? And the answer is potentially yes. And we need to, need to worry about it. And that's about understanding how they were built and why they were built that way and what the implications are. And so when it's particularly viaducts, and viaducts are different, and when they started building viaducts in large numbers for the railways, amongst other things, the centres had to come out quickly and move on to another span or another viaduct or whatever. And they took to filling the bottom half of the arch with masonry or concrete or something that was actually bound material, not just soil fill. And what it took me maybe 5 years to realise is that the bit of arch that's against that solid material is actually stuck to it. And the fact that it's stuck to it modifies the behaviour of the arch in a way that is actually quite serious. And what you end up with is a cantilever piece over the pier, a fourth bridge piece, if you like, with a little suspended span in the middle. And the behaviour is fundamentally different from what you'd expect of an arch because of that.
Okay, interesting.
Yeah? And trying to get to the bottom of that, and so I made the mistake once, so now we've got a new picture of how it might work, but we absolutely have to have proper tests of whether that's truly what's happening before we can sensibly go off on a new thread and say, we need to look at these in a completely different way. Meanwhile, the damage is happening, and there are cracks coming up in bridges, and there are lumps of brickwork falling off. It's an interesting challenge. So there's lots to learn yet.
And technology is obviously a constant through your work, through use of simple solutions to complex problems like the more telltales that you invented, I believe, through to pioneering use of photogrammetry to inspect arch bridges.
Hmm.
It all seems to be part of this constant desire to improve and to learn. Is that a fair way of thinking about your relationship to technology?
Yeah, it's. I can't remember the name properly, the title of the book now. I read a book, 30 years ago, 25 years ago. I can't remember the title anymore. It was something about the war of something in technology at the dawn of the information age. But it was about exactly what computers are. And he said, one of the things in this book, the woman who wrote the book, Stephen Hawking, was giving a lecture at her American university, and she went along and she couldn't get in. She was outside, and they were broadcasting it to the field outside, but she became aware that what she was listening to was a computer, not the person. So did it really matter that she wasn't inside? And exactly what was the relationship of the computer? And the answer in the end is it's a tool, isn't it? And the way I like to think of it is it's a lever for the mind. Yeah? It allows you to amplify your thinking by playing with problems quickly and safely, see what the outcome is. And I worry a lot about the way people use computer analysis, thinking that what it gives them is an answer about reality, whereas what it gives them is an answer about the question they asked, which was not reality. It's a model.
Yeah.
And we need to, for a lot of what we do, we need quicker, simpler answers done many times. Yeah. Rather than months' work to produce an analysis and then just make sure every bit's strong enough.
Yeah.
We need to be getting results every 10 or 15 minutes and thinking, what's the implication of that?
Yeah.
And not starting with a huge model, but starting with something relatively simple and trying to explore it. So yeah, I've loved computers ever since I started working with them during my PhD. I'm endlessly amused about the changes in the world that meant that. So a friend here in Exeter did some analysis for me last week. He has spent a lot of his research time producing some things he calls equilibrium elements. It's a finite element system, but it satisfies equilibrium in preference to continuity. So you get little bits of disturbance in continuity, but equilibrium is satisfied instead of the other way around. And so we were modeling something using these fancy elements. And it was 225 elements, and it solved it it said a second, and what that meant was the lowest unit of solution of time is a second, and it took less than that. And when I was doing frame analysis as a PhD student, I had an 86 node frame, so 86 elements, not 225, and it was bordering on the limit, right? So if you got much over 100, you would never get an answer. And the reason you'd never get an answer was that the time it took to run was longer than something that nobody talks about anymore, the mean time between failures on the computer.
Right.
So you had at least an equal chance the computer would fall over before it got the answer.
Yeah.
And then there was a physical limit, that everything was stored on magnetic tape. It was a tiny memory. Stuff was being read backwards and forwards off these tapes at a frantic rate. And it was actually in the manual that if you got to 300 nodes in this framework problem, the tapes would wear out before you got an answer.
Wow.
You'd wear the magnetism off the tape.
Extraordinary.
And being part of that progression has been fascinating.
And it's something I've encountered with more senior members of the profession regularly, is that actually the early days of analysis taught you how to make excellent analysis software choices and modelling choices, because you were so limited in the technology that you had, and yet those skills that you develop to deal with those constraints are actually still incredibly valuable in the way that you approach modelling now.
Yeah, and it isn't taught enough anymore, I don't think. There isn't enough. Have you put a rough check on this?
Yeah.
Okay, it's a 50-story building, and every joint's been modelled and all the rest of it. But you can actually just do a quick hand calculation here and see whether the answer you've got is in the right order of magnitude. Because if it isn't, then you've got something wrong, and you need to know that you've got something wrong.
And know why.
And often it's hidden. And I mean, one thing that doesn't happen quite so much anymore, but people pretty much had to partition their structures. You had to, if there was any chance of using some symmetry, then you had to cut it down the symmetry line and put some boundary conditions there that represented that symmetry. And I don't think I've ever seen an analysis run the first time in which those boundary conditions were right. Yeah, they are really hard to work out.
Yeah.
And it involves getting your head around that 3D business again.
So aside from the structural engineering aspects, many of your projects are known for your use of aspects that draw on kind of unconventional elements or things that are out of the ordinary during construction, or even just the methods that you use to access and inspect site. What drives that level of experimentation? Is it a need to know why and how, or is it just that the first principles approach is proven through your experience to get to a better solution faster?
Well, first principles always, in my view, always gets you to a better solution. Not necessarily more accurate, but where you know where you stand. So something that I was talking about recently is that in engineering, we know we're not going to get the right answer. We need a conservative answer. In order to get a conservative answer, you need to understand what conservatism is. In this particular circumstance, what is the conservative thing? And it may not be to make it thicker. Right here, it may be that letting go of some of that stress and letting it go off somewhere else is the right thing to do. So that sort of level of first principles thing is clearly important. But the other thing is just I'm a gadget freak, aren't I? Oh, here's a new toy. What can we do with this? The photogrammetry thing is interesting. I was fascinated with it from first learning about it in surveying classes. And I've watched it coming towards me. And I suppose 15 years ago or so, no, actually longer ago than that, before I left Dundee, actually, so mid-90s, I came across the first attempt at digital photogrammetry. And there was a guy at Newcastle University in Australia who developed a little machine that meant that you didn't have to take standard parallel photographs. You could do this sort of thing, and you could then put these two pictures into the machine using 6x6 negatives, actually, or transparencies. You could put those into the machine, and you could steer the machine around and say this point and this point's the same, and this point and this point's the same, and this point and this point's the same. And you kept doing that, and suddenly it goes zip, zip, and suddenly you'd have a little three-dimensional view of a local patch. And then you could start plotting, and it was very effective. It was not trivially cheap, but it was quite effective. And then people came along with things, so digital cameras came in, and that transformed everything, because in a digital camera, the relationship between the pixels and the center of the lens is the same in every picture. So you don't have to go in for putting fancy pieces of glass in to hold the film against and stuff like that. Just, it comes free. This pixel is in line with that point over there, and the story, and people started to develop that. And then the development seemed to stop. And about the time Hamish joined me in 2011, I said to him one day that, you know, it seemed to get stopped. People are still doing the same thing, and everything's just stopped. And he came back a couple of hours later, having doodled around the web for a minute or two, and said, "You're just using the wrong words." What do you mean I'm using the wrong words? Photogrammetry is photogrammetry. Not anymore, it isn't, he said.
Right.
It's been picked up by the games people. They've done it from scratch without ever going back to the old photogrammetry stuff. They've just picked up this idea and run with it, and they now call it structure from motion. And if you look for structure from motion, you'll find at least 3 different programs.
Wow.
And it's just completely automatic. You just go click, 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 and throw it at the computer, and the computer comes back and says, "Yeah, I can deal with that. Here's a model." And that, at that point, then becomes completely transformative, because you can get a camera to effectively hands clutch of every part of a bridge much more easily than you can get a person there. And having built a 3D model, you can then sit in the wall and you can zoom backwards and forwards across it.
Yeah.
You know, you say, "There's a crack here. Did I see one in that corner?" Yeah?
Yeah.
Whereas even if you're just walking around under a bridge, that takes long enough that you're no longer actually sure that the crack you're looking at over here is the same as the one you were looking at over there. So yeah, it is transformative. But the mirror image of that is that my view of bridge inspections at the moment is that they are not fit for purpose. You might as well not do them, because the separation between what the real problem is and the quality assured process of producing a report is just so wide that the two don't meet, and it's going to end up with something falling down.
So you are suggesting that the photogrammetry gives you a handle, but without that understanding of the structure and what's going on, there is almost no point in making the model.
There's almost no point in making the model, but one of the threads with the model was that one thing that I wanted to do was to use the models as a teaching tool. So, you know, I can now say to somebody, "Here's a model of a bridge, inspect it, write me a report." There's no risk assessment, there's no expense of going to site and all the rest of it. Yeah, here's a model, just explore it.
Yes.
Yeah.
Yeah.
And I haven't got there yet. I haven't got the teaching tools together, but it's clearly a worthwhile thing.
Absolutely, clearly some potential there.
But if you, these bridges are old. There is nobody alive who built one. The information is lost. It isn't lost, actually. If you dig hard enough, you can find it. So, and we need to understand how they were built in order to understand how they're behaving. And sometimes we can work out how they were built from the way they're behaving if we recognize that interaction. But you're not going to get a graduate learning that about a material they've learnt nothing about and a bridge type they've learnt nothing about by either sending them to site to inspect the bridge without any prior training, or giving them somebody else's inspection and just saying, "Analyze that." Yeah? But you have to teach people how to look for a start. Yeah?
Yeah.
One of my favourite sayings, a friend Paul Beckman, who for a while was head of R&D at Harvey, said at a conference I was at once, and I mean, first of all, let's say masonry bridges are heritage structures. And essentially, he said that inspecting heritage structures requires 2 open eyes and 1 open mind. Yeah, and that goes along with, was it Pasteur who said that fortune favours the prepared mind? Yeah, that your mind has to be prepared in order to see what's in front of you. And if it isn't, if you haven't had the preparation, you're not going to see it. So one of the questions is how to get that attitude of mind and way of seeing out there in the field.
And is that your next challenge? You've said that retirement's not an option. Is engineering going to sustain you for many years to come?
Well, this problem with the viaducts is going to keep you going for 5 years anyway. I am now starting to write a book, and that's quite interesting. And working out how to write a book that will both interest and educate people, preferably with the education remaining well hidden until hard to use it.
Yeah.
And that leads you into finding things quite by chance. So it's the sort of serendipity that puts something in front of you new. So some years ago, I had a spare hour in London and wandered into the library in the Civils. I knew Mike Crimes, who was the librarian in those days. He said, "Oh, you got a little bit of time, Bill? I've got a few books that you might like to see." And he kept running off to a shelf. One of the things he came back with.
For podcast listeners, I'm being shown a very old French volume.
Isn't it? Yeah. Building bridges in the 18th century, and it's full of
extraordinary pictures or drawings, construction drawings of
construction drawings. Yeah, and this guy, Monsieur Perronnet, was the head of the School of Bridges and Roads in Paris, but he was also building bridges. And in order to preserve his understanding, he produced this book. And for several bridges, there is a full page showing exactly where the bridge has got to at this point. And there are also detailed drawings of all the machines that he built to do the mechanical work. This is what the pile driver looks like. This is what the horse-driven barrel driver looks like. This is a concrete mixer. Here's a cement mixer. All these things. And I was trying to write up some of that and turning it into a chapter of the book. And then, because I never learned French, I can't read the book myself. But okay, Google can translate it, and mostly it's the pictures. But I was concerned about pronunciation. I have a friend who's a professor of French at St Andrews, and I got her to help me with some pronunciation to produce a little bit of video about this, which will be on the web shortly. And she said, "And what about the memoir?" I said, "What memoir?" I said, "Well, the memoir on centering and decentering of arches." What? Where?
Wow.
And it's just wonderful. There's just so much stuff there about why he did. I mean, so he built flexible centres, which meant that he had to balance the loads all the time to keep everything steady. And he did it because he was very concerned about putting too much support in one place and actually disturbing the shape of the arch. And then the casual way, he says, they work in feet and inches, of course. In the 18th century France, just the same as us, they work in feet and inches. Casual way, and when they took the centering out, the bridge came down about 11 inches while we were taking the centering out, and then another 1.25 inches over the following year. And it was really quite handy because it reduced the size of the ramps we had to build to take people over the bridge.
An extraordinary change in geometry over the construction period, but I suppose
Yeah.
it's a
Yeah.
fantastic. Well, it feels like a really good place to leave it, Bill. Thank you for a fascinating conversation, and I hope that listeners have enjoyed tuning into parts of Bill's career, and we will look forward to Bill's memoir as and when it's available. If you'd like to know more about Bill and his work, please head to his website, www.billharveyassociates.com. His fantastic regular emails, Bridge of the Month, are worth subscribing to and reading avidly. And there's many more aspects that he's communicated over his time and his career. Bill is a member of the Executive Committee of the British Group of the International Association of Bridge and Structural Engineers. IABSE is a group of designers and engineers that are passionate and inspired by the world around us. To find out more, head to our website, www.iabse.org.uk. Thank you very much for listening.